talking about time result photoemission.
All right, thank you very much. And also thank you for asking me to come to this, this wonderful workshop. I'm going to be talking to you about some work that I've done in collaboration with Tom Devereaux, Lex Kemper, who is in the audience and will be giving a talk a little later in the session, Brian Moritz, Sona Najafi, and Michael Sentev. And I'm going to apologize. It seems like I'm getting cut off a little bit on the top and on the bottom, so hopefully it won't be too bad. But I think a number of titles are going to be missing, and hopefully we don't lose too much stuff off the bottom either. There are a number of papers that have come out recently where we've been reporting a lot of this different work, and of course we have to acknowledge our funders, which is the Department of Energy. So one of the first applications of ultra-fast was 130 years ago or so. Leland Stanford, at least the way the legend works, although I've been told this might not be a completely true story, but apparently Leland Stanford had a $25,000 bet with someone else who was also obviously very wealthy. I think at the time Leland Stanford was kind of similar to what Donald Trump is today for us. He actually hired this guy Muybridge and offered him the $25,000, he was so sure he was going to win the bet, to prove that the horse's hooves left the ground during a gallop. The motion was so fast people couldn't really see it. And it took him about 5 years, primarily to figure out how to make a shutter on a camera that was fast enough that he could capture the motion. And then he set up tripwires along a track so that as the horse went by, it pulled a little trigger and the camera snapped, and he took a whole bunch of these cameras in motion, and you can obviously see here that all the hooves are leaving the ground at some point during the motion. And he then, perhaps a little bit controversially, also started filming a lot of animals, including humans, and I think the humans were nude who he was filming in motion. That was the controversy. And he published 2 books of animals in motion and humans in motion. And this is actually the beginning of motion pictures, because if you take his pictures and you put them together, this was supposed to just start. So something's not quite working with this. But anyway, maybe if I click on it here, there we go. All right. So if you put those together, you can see that you get a movie. And the idea behind this is that if you really want to study complex dynamics, you have to observe it on the appropriate time scale. So if we move forward now into more modern times, most people have seen these kinds of pictures. This was invented by a person, he's right down here, named Edgerton from MIT. It's called microflash technology. That could pin things down to the order of nanoseconds. And so it was typically used not for movies, but for still images of things, because you really can only get one shot, and the key was getting the timing right. So you get the beautiful shot like what happens to an apple when you shoot a bullet through it. Now you come to a number of years later, 2008, and here we have a movie that is on a femtosecond time scale. This is a movie of angle resolved photoemission in a material called terbium tritelluride. The gap along the Fermi surface is in this region here, and this is a scale that's showing the time. -200 is before the pulse center is sitting here, and so as this is driven, it goes from being gapped to having a gap that fills in, and then you can see there's a little bit of an oscillation, and then the gap starts, the filling in of the gap starts to recede, and the gap reforms a bit of time after the pump itself has been finished. So now we've gotten to the point where we have movies that are on tens of femtosecond kind of time scales. So what we want to be able to do as theorists is try and understand and explain what's going on with those kinds of measurements. And because these experiments involve two kinds of light. The first light excites the system into non-equilibrium with a pump, and then you come with a later light that's a probe that's going to detect what your pump excited. And so those of you who've never seen this thing, it's called the Kadanoff-Bain-Keldysh contour. I can explain for you very easily where it comes from. If I write an operator in the Heisenberg representation, we'll have a U operator here and a U dagger here. And so U means operate forward in time, so this goes forward in time from whenever I start to time t. Then I have a U dagger, but I also have a U here. And when you combine the U with the U dagger, it says go from time t to time t prime. So I'll go forward from time t to time t prime. And then I have a U dagger here. Well, U dagger says go backwards in time. So then I go backwards in time, all the way back to here, to where I started. And then I have this thermal factor, which I can also replace by evolution along an imaginary axis of length equal to beta, which is 1 over the temperature. And so that's the actual origin of this contour. And we have to solve problems with this contour because we don't have time translation invariance anymore. The vector potential that describes the field is on for some period of time, and it's off at other periods of time. And so there's some non-trivial origin of time in this case because things are now changing with time. And as long as you can formulate your theory in this fashion, you can calculate things like this object, which is called a lesser Green's function. And the way that we introduce the field is via something called the Peierls substitution, which involves taking the momentum and shifting it by the vector potential. And I'll just give a little bit of a caveat here. We're assuming that we have a spatially uniform, time-dependent electric field. And those of you that have taught or taken a classical electromagnetism class say, oh, that violates Maxwell's laws. And indeed it does violate Maxwell's laws. I can't have a uniform time-varying field. I'm also ignoring the fact that when I have a time-varying electric field, it will generate a time-varying magnetic field. All of those effects are smaller, weaker effects that are not as important as the dominant effect, which is driving the electrons with the system. And once we do something like remove the translational invariance of the system, then it becomes very, very difficult to solve. So these problems are hard to solve already. So that's one of the approximations that always goes into almost anyone who talks about non-equilibrium. They'll use a spatially uniform field, and they'll ignore the magnetic field associated with the time-varying electric field. Okay, so here's a schematic of how that works. There's some pump, and then there's some probe with some time delay. If it's photoemission, I typically think of having a low energy pump but high amplitude. So low energy in terms of the frequency of the photons, like infrared or possibly optical. But then I'm going to have a pump that has to be something like ultraviolet because I want to be able to photoemit electrons. And the initial idea was, let's use this pump to sort of excite into the unoccupied states that I can't see in regular photoemission. But if I pump it too much, in addition to just exciting the states, I'll also change the states because it'll get dressed by the effects of the field. And so this is what you see happening here. You start in equilibrium. As you fill in the states due to the pump, you see I get states filling in these regions, and then after you wait for a long period of time, these relax back down to something that looks very similar to the initial equilibrium, but it is a little bit different. And the formula that you need to use for photoemission involves a 2-time Fourier transform of this lesser Green's function. The Fourier transform factor is here, and then it gets weighted by the probe envelope, this function here, both as a function of t and as a function of t prime. And if you plug into this formula, it's by no means obvious, but it turns out that this object is manifestly positive, and of course a photoemission spectra is manifestly non-negative, and a photoemission spectra has to be manifestly non-negative as well. So this satisfies that property for photoemission. And for those of you that have studied photoemission in equilibrium, the G lesser in equilibrium is just the retarded Green's function multiplied by f of omega. And so that's exactly what you would normally say photoemission is measuring. All right, we're going to be studying the electron phonon problem. I can see my title is completely gone up there. But the model that we're looking at is a Holstein model, so it involves electrons that will hop on the lattice. There are Einstein phonons that have a particular frequency on this lattice as well, and then there's a coupling between the electron charge and the phonon coordinate. And this is all you need to get all of the standard kinds of electron-phonon behavior. You get a renormalization of the electronic quasi-particle near the Fermi surface. It has superconductivity as one of the low-energy states. It also has charge density waves as one of the low-energy states if I have nesting. And so you can get all of the kinds of standard electron-phonon type behavior just out of this simple model. So I want to talk a little bit about the standard kinds of electron-phonon behavior that you get in photoemission. Here on the left-hand side, I have for you plots of the imaginary part of the self-energy for a normal state electron-phonon system. This is the imaginary part. This is the normal state at low temperature. This is the normal state at high temperature or higher temperature. And this is the superconducting state at a low but not zero temperature. And what you can see is that because I can't scatter anything by the phonon if the electrons have energy less than the phonons, there's no scattering until the electron energy gets big enough that it's larger than the phonon energy, then it can scatter. So it's zero here until it can scatter, and then I get some scattering rate associated with the scattering from the phonon. And because this has a very sharp structure, when I do a Kramers-Kronig to the real axis, I get these sharp features in the real part of the self-energy. If you raise the temperature because there'll be some thermal phonons present and because the electrons will have a more spread out distribution, the phase space restrictions become less severe, and so this gets smoothed out a little bit, which means these features are smoothed out a little bit as well. If I go to the superconducting state, not only do I have to have energy bigger than the phonon energy, I also have to have energy bigger than the superconducting gap, so it widens, and then you get this classic BCS structure that is appearing due to pileup of density of states from the superconductivity in the imaginary part of the self-energy, and that gives rise to additional features, sharp features, in the real part of the self-energy. And what that does, if you plug that in and say, all right, let me see what does a photoemission spectrum look like, it gives rise to this behavior that's called kinks, and you can see if you follow, this is momentum here and this is energy, if you follow a curve that would be a dispersion curve, you can see the slope is changing at these places where the arrows are. And so, perhaps not so easy to see down here, but pretty clear over here. And these kinks are occurring precisely at the places where you have this structure coming from the self-energy. There have been a lot of studies as well on time-resolved photoemission in a number of different materials. I'm going to focus primarily here on some studies of high TC superconductors. And here, this is before the pump, and then this is the time delay getting bigger and bigger as I move down the page. As you pump the system, you remove particles from low energy and you put them at high energy. And so I start depleting here and adding particles here, and then after the pump is finished, these particles start coming back as they diffuse back, and eventually I get something that looks kind of like what I started with. If you look at a difference between the initial state and the state as a function of time, that's plotted for you here. You can see this kind of difference. I remove particles and then I have more particles present, and then as a function of time, these guys both shrink and come towards zero as the system redistributes itself. You might also notice that in this particular case, the excitation isn't precisely conserving momentum because I've taken more particles out at a particular momentum, and I haven't excited all of them just to that momentum. Some have gone to some other momentum as well, and that could be because they scattered or other things have happened to them. If this is summed overall momentum, obviously whatever I excite has to, whatever I remove has to be excited because I'm not creating particles anymore. So then, if you look here at a photoemission spectra, what you see Once again, I've showed you a picture that looks like this. This is the equilibrium picture with the Fermi energy here. There are these two lines here, which I'm going to focus on in just a minute. They are shifted by the phonon frequency. What happens when you pump it is you very rapidly excite particles up to fairly high energies, but then they very rapidly come back down, and then the scattering inside this window is much slower because, once again, the phonon energy is omega. It's more difficult for the electrons to relax energies that are less than omega. The scattering rate tends to go down in there, and so it takes a much longer time for them to relax. And here are some pictures of those differences that are shown, first at low temperature and then at high temperature. The effect is much bigger at low temperature, where I have a larger number that are excited, that are depleted and excited, than what happens at high temperature, where the effect gets smaller. This is a theory calculation, and so in this particular case it is momentum conserving, so exactly what I deplete is excited in this particular case. All right, so it's non-equilibrium. We want to really give it a lot of power, and we want to really drive it into non-equilibrium, not just study quasi-equilibrium. So you can really hit this with very intense lasers, and when you do that, this is a theoretical calculation. It's showing this relaxation as a function of time. So this is delay time, and the pump is occurring centered around 0, and you can see that you're exciting a lot of electrons, and then very, very rapidly those electrons relax into this phonon window. And then it takes them a very long time to relax when they're inside the phonon window. And here what we have are cuts along these directions for these different plots here. These are ones that are outside the phonon window. They relax very rapidly. These are ones inside the phonon window. They relax much more slowly. And so here we have two movies, which hopefully both will start. Over here we have more of a weak excitation. Here we have a stronger excitation. You can see here this has that kink structure that I was talking about before. It's a very pronounced kink structure. In the weak excitation, I'm sort of exciting up, and this is getting perhaps a little bit smaller of a jump in the slope, but nothing like what's happening here in the strong excitation. It looks like that slope is really getting stretched out as they're getting excited. And in equilibrium, this slope is a measure of the strength of the electron-phonon interaction, the kink, the change in the slope. And so you might ask whether or not this driving to non-equilibrium is actually weakening the electron-phonon interaction. And you might think that, well, that could obviously occur. It could change the way that the screening is occurring and other things like that. So this has actually been seen in experiments. These are some experiments from Uwe Bovensiepen's group. And here they're looking at the change in the slope, and it's about a 10% effect in this particular material. Excuse me. And so the question is, what is exactly happening here? Is this actually a decoupling of the electrons and the phonons? What happens here is, as we mentioned before, you have this slow scattering rate inside this phonon window and a fast one outside. When we go to non-equilibrium, that gets relaxed. And what happens is the scattering rate becomes less when I'm far outside, and it becomes higher when I'm inside. And that can be understood from a simple phase space argument. What I want to focus on is actually the integrated weight inside this imaginary part of the self-energy, which you can view as a measure of the strength of the electron-phonon interaction. And so here I've taken the difference between these two. This is looking at an equilibrium versus a pump non-equilibrium case. And red means that the green is below the blue, and blue means that the green is above the blue. And so here I have where it's getting larger, and here I have where it's getting smaller. And if I take these guys and separate into two windows, outside the phonon window and inside the phonon window, and go ahead and calculate those integrals, those are the green and the blue curves here, but when I add them together, you see I get a completely flat curve. And so there's actually turns out that there's a sum rule that the self-energy satisfies. The first moment of the self-energy just depends on the phonon fluctuations of the coordinate and whatever the electron-phonon coupling is. So if the electron-phonon coupling doesn't change, there's actually a sum rule. So even though it looked like there's a weakening of that electron-phonon interaction, that just is happening because of phase space changes in the way that the electrons and photons are scattering due to the fact that they've been excited into non-equilibrium, and is not due to some kind of transient change in the electron-photon coupling. Okay? If the electron-photon coupling is weak, it turns out that that relaxation time is very closely related to the relaxation time that you would get from the equilibrium self-energy, and this is a comparison of the equilibrium self-energy with what you would get from the relaxation rate, which are these orange symbols. Ignore the green ones for now. But when I go to non-equilibrium, this changes rather dramatically. I get some extra structure, and it typically occurs with some kind of a peak that's occurring at the very low energy that's occurring in non-equilibrium that is changing a bit. Nevertheless, the total integral over here for the total electron-photon coupling strength is remaining conserved. So what is determining this relaxation rate? It's not just given by the self-energy, and Lex is going to talk about this a bit more in detail in his talk. This is a comparison of some calculations for a Holstein model or a Holstein-Hubbard model. The line here is what you would get for the equilibrium self-energy, and these different plots are what you get when you analyze the relaxation rates at different times in the relaxation of the system. And you can see it's very similar to the self-energy, but it has some marked differences. In addition, a lot of times you've probably heard of things called hot electron models, which say that I take my electrons, they rapidly scatter with each other, they create a hot electron gas that thermalizes amongst themselves, and then only over time do they thermalize due to interaction with a bath, like the phonons, to get down to whatever their final temperature is. Well, it turns out that picture can't be correct either, because you always have a different distribution function for the Green's function and for the self-energy, and that's plotted for you here. So if I plotted the G and the sigma for you here next to each other, you'd say, they really look like they're the same. But here, this is the ratio of the two, and you can see they're almost identical down here at low energy, but up here at high energy, they're quite different. And so it's actually this difference in the distribution function between the self-energy and the Green's function that actually drives the further relaxation. And it turns out that if you gave the same distribution function for the self-energy as you did for the Green's function, like an f of omega, which is what you would do if the thing had thermalized, you get no more relaxation even if it's at a hot temperature. And that's an exact result you get by looking at the many-body equation of motion of the system. And so it turns out that this relaxation is a little bit more complicated. We still don't fully understand it, and Lex is going to talk a little bit more about that. What I want to get into in the remaining time that I have is just talk to you a bit about what happens when we go to the superconducting state. And there have been experiments that have been done. These are optics experiments which have seen Higgs oscillations. But I'm going to focus instead on what you can see with angle-resolved photoemission. This is what you have in the normal state. When I go to a superconducting state, this gets pulled down because of the gap, and there is a bit of a change in the slope as well. But when I pump the superconductor, it starts to look back like the equilibrium again. This marker is occurring at the peak of the ARPAS signal at the Fermi energy. So here's a movie of what that photoemission looks like as a function of time. Now it's getting pumped at a very early time, and that kind of very slow oscillation that you're seeing in there, that is the Higgs oscillation due to the Higgs mechanism. And so what is happening there is you're getting an oscillation whose period is going like 1 over the or 2 over the superconducting gap, and I'm going to show you in detail where that comes about in just the next couple of slides. So here, there's a couple of different ways that we can try and pull out where this Higgs, that it really is the Higgs oscillation that's occurring. So we focus at that maximum on the Fermi energy as a function of time. You can see by this orange circle, it's oscillating. And that actually comes out to be a curve that looks like this. If you actually figure out from this what the period is of that oscillation and compare it to the gap that the system has, that has been reduced from the equilibrium gap because I pumped energy into the system, so the superconductivity got reduced, you find that there's an exact relationship between those. You also can see it in the anomalous average. This is more of a theory calculation. See, here's where the pump is, and that's the frequency of the pump. And this is the frequency of the Higgs oscillation. They're completely and totally different frequencies. It's not like this is something where you know, I just hit it and it's responding with the same frequency that the light had that I shined on the system. It's a completely different phenomenon. Much slower oscillations are occurring for the Higgs. And so here, if we look at a bunch of different amplitudes for the electric field that we apply on the system, the key is that there's a sweet spot. If I hit it too little, I don't excite enough of the Higgs oscillation because it requires a nonlinear excitation to see a Higgs oscillation. And so I don't see anything in linear response. If I hit it too hard, I destroy the superconductivity. And if I destroy the superconductivity, I also can't see the Higgs oscillation. So I have to get it right in a sweet spot where I hit it hard enough that I'm outside of just linear response, but I don't hit it too hard that I completely destroy the superconductivity. And inside that range, then this is the oscillation of the peak in the photoemission at the Fermi energy, or the Fermi wave vector. And you can see, depending upon what the amplitude is, this period is changing. And in fact, this is a plot of that period as a function of the fluence of the signal measured by the maximum of the electric field. And you can see that it's changing exactly in accord with what it would do for a Higgs mode. So with that, I'm going to put on my summary. I've told you a bit about time domain spectroscopy, some of the things that can be measured with it. Talked a little bit about the theory and how we describe it. And I've given you some examples both in the normal state and also in the superconducting state, including how you can actually see Higgs oscillations, or we believe you can see Higgs oscillations in time-resolved and angle-resolved photoemission. So far, it hasn't been seen in the photoemission, but it has been seen in optics. And so hopefully it'll be seen soon in photoemission. And once again, I'll flash up my collaborators, and then if there are any questions, I'll be happy to answer those as well.
All right, the talk is now open for questions. Yes.
Yeah, well, to clarify, the Higgs oscillation is a frequency smaller than the gap. What you see?
I think it's twice the gap.
It's the twice the gap. Okay, then it should be overdamped. Then it typically should be overdamped, and you shouldn't see many oscillations.
It should be what?
Overdamped.
Overdamped.
Due to quasi-particles.
It turns out that it's not, at least in terms of this angle-resolved photoemission, it certainly looks like it is over-damped, but it looks like that damping rate is not very high. I mean, if you look here, we can only run these calculations out so far in time. Of course, this is still only 250 femtoseconds, so it's not a very long time. But these aren't really getting quenched very rapidly.
Yeah. So this 0.9 red curve looks like it will have many oscillations. However, it's on the top of the density of state, right?
No. This is not an oscillation on top of the density of states. This is an oscillation of the peak. If I take a distribution, I do a cut at KF. I look at an energy distribution curve at KF, and I look at the peak of the energy distribution curve. That's what this oscillation is.
Yeah, but the frequency of it, if I calculate the period from here, will be 2 delta, right?
Yeah, that's what this is showing right here.
And that's what
it's 2 times the effective delta that I have because I pumped energy in the system. I've reduced the superconductivity.
Well, maybe we'll follow up.
Yes.
And you were mentioning that you need a certain pump energy. I think what the point is, you have to break the particle symmetry, and then you see the Higgs. Otherwise, that's what I think. Why you need a certain excitation.
Well, it's well known that the Higgs does not couple to the electric field in linear response. So if my field is too small, I simply don't see it because I'm in the linear response regime. On the other hand, if I pump too much, so I no longer have superconductivity in the long time state that it's going to, I'm not going to see the Higgs oscillation either. So that's the reason why I have to have this range. I don't think it has anything to do with particle hole symmetry per se. It's more the question of I need to pump strong enough that I'm actually coupling the Higgs, but I can't pump too strong that I get rid of the superconductivity or the whole effect disappears. Yes?
I guess I also wanted to follow up on this exact Higgs mode to solve the error.
experiment, it was the frequency of the pump, but certainly in the theory that we've worked on, the frequency of the pump does not play very much of a role in that. I think the reason why, in their case, it did play a role is that if, given the fluence that they were applying, once they apply above the gap, they were applying too much, so they were killing the superconductivity, so they couldn't see it there. So they could see it underneath. When they were pumping underneath, they weren't exciting the electrons as much, and then they could see the Higgs oscillations.
That's my point, is that experiment that they did was done with various conditions in the sense that their pump was actually exceedingly weak. And the more important part of it was that it was less than half of the superconducting gap. So once they had to be well enough lower to minimize the air rate. But that field they used was extremely small.
Well, I mean, this is just something that, I mean, we haven't done the calculation for what happens in optics, so I can't immediately say to you what happens there. But the ARPA seems to be much more robust against that. It doesn't require pumping at a frequency that's exactly half or close to half of the superconducting gap. It doesn't seem to require any of that. It's kind of like the question of any kind of oscillator. If I hit the oscillator with a hammer, it's going to oscillate. I don't have to hit it, I mean, as long as I impulse it, I get an oscillation that comes out. And that's just generic about most oscillators. I don't really know the details. I'm not a huge expert on that kind of optics experiment as to why they had so much trouble with that.
If you convert something like this to a excitation density,
Excitation density.
how many photons per unit cells?
Yeah, we have a little bit of trouble, I think, going from our theorist amplitude to an actual experimental fluence. But I mean, it might be possible, but that's not, that's the really slippery connection that we have.
Next, gentleman.
Granted, optics experiments, part of what happens at the moment that they hit some delta in their experiments, their signal gets swamped by normal absorption. So you can actually still see the oscillations once they go above 2 delta. They're still in their data. If you look carefully, it's just very hard to see. Right, so I'm not convinced that you pump a load. The second thing is, what Jim said here was the point, is that you put enough fluids in, put enough energy that you melt the gap partially. So that's material dependent. Right, so you can go look, for example, in the Freericks at someone's work at Lazard, where they've melted the gap partially. That's sort of the fluids you want to be at, but that's what it is. And if you want to do, say, NGV2 or K to 60, you might do it.
Hoopers will be completely overdone.
Sorry?
Hoopers will be completely overdone. Too many possibilities.
No, you're thinking of these oscillations as a whole in some type of frequency. That's not what this is. This is very different.
All right. Well, in the interest of time, let's.
Not a club.
All right. Let's thank the speaker once again. Great discussion.